about sporadic points on X1 and N.
Thank you. So I have to say that I haven't given that many slide talks, so I may go fast. If I go fast, you should just stop me. But I shouldn't. And I also don't know very well how to use this, so hopefully it will work. All right, so today I'll just talk about elliptic curves, basically, and their torsion subgroups. And again, yeah. So for me today, an elliptic curve will be given by a cubic equation where we have y squared equals some cubic polynomial given by f of x. And we want this curve to be smooth, so we want f to have no repeated roots. And we'll say that if we take a point on this curve, x comma y, if x and y are given in a number field k, then we call it k rational. And then E of k denotes the set of such k rational points on E. So this k, when the k is q, then we say just rational points. And then somewhere in the talk we'll say non-CM curves. That just means that so an elliptic curve over a number field can have an isomorphism ring as z or something a little bigger. And so if it is strictly bigger than z, then we call it CM. So elliptic curve with complex multiplication. And so here's an example. Then if you take the elliptic curve given by y squared equals x cubed minus x, this is a CM curve because we have this extra automorphism of order 4. And so in this case, the endomorphism ring is z adjoint I. So elliptic curves are special in the family of curves in a way that we can define an addition on the set of points on this curve. So this means that if we take 2 points on an elliptic curve, then we can define the third point. So let's say that this is my elliptic curve E, given by y squared equals f of x. And if I take 2 points P and Q here, hopefully I'll manage to make it. Then if you draw a line between these 2 points, since it's a cubic equation, it will intersect it at another point, which I'll denote by P star Q. And if you take the symmetry of this with respect to x-axis, then you will get P plus Q. So this addition is abelian, and it actually forms a group. So if I look at the set of points on this elliptic curve, with this addition, I get inverses and identity element. And the Modular theorem says that it's actually finitely generated, which means that it doesn't have to be finite, but at least I have a finite subset of the k rational point so that it generates the whole thing. And so the finitely generated abelian group just means that we have the infinite part and the finite part. So we call the finite part as the torsion subgroup, and that's the part that we're going to talk about today. All right, so here's an example that I have this elliptic curve y squared equals x cubed minus 4x. And if you look at just set of q rational points, we get this torsion subgroup as z over 2z plus z over 2z. And the rank is 0. So in general, since it's an abelian group, you can talk about the multiplication by n map on this group. And that's going to be a group homomorphism, so you can talk about its kernel. And we denote it by en. All right, so then naturally we can ask the following question, that if I fixed an integer d, what can I say about the torsion subgroups of this elliptic curve over any number field of degree d? So the elliptic curve can be any curve here, and the number field can be anything, just I'm only fixing the degree of this field. So then what can we say about it? The first answer is given by Mazur, and I'm looking at the number fields of degree 1, which is just rational numbers. And in this case, we actually get a very limited list, right? We have 15 groups, and the highest order that I can get is 12, but I don't get 11. So there are going to be some magical numbers appearing in this talk. That 11 is, I guess, one of them here. So this is a very active research area now, defining the torsion subgroups over different degree number fields. And so after Mazur, his student Kamienny with Kenko and Momose, they answered the question for degree 2 fields. So for quadratic fields, the list is a little bigger, but it's still finite list. So we have 26 groups, and I think this 26 is not related to 26 sporadic groups. It's just random. And so here we can have a cyclic group of order less than or equal to 18, and the highest order appears here is, I believe, 24, the size of the group. All right, so here the elliptic curve is arbitrary and the quadratic field is arbitrary. So then right now there are different research going on with cubic fields, but I believe that the only complete classification is given for the field of rationals and the quadratic fields. So even for cubic fields, it is known what sort of groups can occur infinitely many times, but we don't know if that's the complete list. And so in particular, then I can say in this list that every group here occurs for infinitely many elliptic curves over possibly different quadratic fields. And the same thing for Mazur's list. That, yes?
Break down at all if you look at like imaginary quadratic fields versus real quadratic fields, or is it
I don't think it's done.
all the same? Oh.
Yeah. So I think the only result that I know that Neumann did, if you fix your field as q adjoint I or q adjoint square of negative 3, so quadratic cyclotomic fields, then we know the list, and it's actually very close to Mazur's list, and you only get 2 extra groups. But I believe that that's the only classification that is known. And so in general, we actually know sort of a similar answer for any degree D. We don't know what groups can occur, but we do know the bound on the torsion subgroup. And so that's given by Merel. This is called the uniform boundedness theorem. And so in this case, we take an elliptic curve defined over any number field, and I just fix the degree of this number field. And I know that there is a constant that depends only on the degree of this field, such that the torsion subgroup is bounded by, the size of the torsion subgroup is bounded by this constant. So this is pretty strong, and but this constancy is not very efficient. So in general, it's big. But and I don't actually remember what the bound is in this case, but there was an improvement. That we know a better bound now, that if I only restrict myself to the points of prime order p, then p is less than or equal to this number when d is not 1. But this is still not very small. So perhaps this is why people are still trying to sort of classify, like for certain degrees, what kind of groups we can get. But I will suggest a better question in this talk than that. All right, so then we can ask, what is the method? How do I understand if I just take a number field and what kind of points of order I can get? And what do we use for that? And so for that, we'll talk about the modular curve x1 of n, which also appeared in the title. Do you have any questions so far? No. All right, so then, so questions like this, we look at the modular curve. Here, I actually don't talk about x1 of n. So we have the upper half plane. And if you look at the isomorphisms of upper half plane, we take this subgroup of it called gamma 1 of n. And if you look at the action of this group gamma 1 of n on the upper half plane, this gives you a Riemann surface. It's not complete. So this is an open Riemann surface, and we call it y1 of n. So in fact, that any point on this Riemann surface will give you an elliptic curve and a corresponding point of order n on this. And so this is not compact, and if you want to compactify it, then you would have to add some cusps, and then what you get is normally known as x1 of n. So the correspondence is that if I take a point on this y1 of n, so it's a Riemann surface, so it's an algebraic curve, and it has a certain equation. So I just look at the solutions to it. And if I just take a number field k, and if I take a point on it, then that point will give me an elliptic curve defined over this field k and a point of order n, again defined in this number field. So this is the correspondence that we need. So then using this, we can actually formulate Mazur's result and Merel's result in terms of x1 of n as the following. So then the Mazur says that the modular curve y1 of n has no rational points when n is greater than 12. and when n is 11. And in fact, it says more that y1 of n has infinitely many rational points when n is less than or equal to this bound. And so we can say something about the Merrill's theorem. Then it says that we have a constant c depending on this degree d, such that y1 of n has no points of degree d for n greater than c. So here I have to explain what a point of degree d means. It just means that if you take a curve and I take a point on it, and then I look at the coordinates, if the coordinates are defined over some number field, and I look at the degree of this number field, and that's the degree of this point. All right, so Merrill's theorem says that here I have a bound, and after this, if I go above it, then I won't get any points. So, and in my title, I said sporadic point. So there, I'm sort of interested in the values of n, where y1 of n has some points, but only finitely many, which I'll define now. All right, so a point on an arbitrary curve C is called sporadic if there are only finitely many points of degree less than or equal to degree of this point. I'll give you an example. So in this talk, I'm not going to talk about the sporadic points on an arbitrary curve, but on x1 of n. So before we talk about sporadic points, we can sort of talk about when we have infinitely many points, so that we can understand when we have finitely many points. So for that, there's something called a gonality of a curve. So let's say that I have a curve C. Then if I have a map from C to P1, my advisor really liked drawing pictures. When I write something abstract, he always said, just draw a picture. What do you mean by that? So this just means that you have, so you have this curve and then the projective line. So let's say that you have a map here, some rational map, and it's degree d. So this means that for every point here, above each point, if it is not a ramification point, then you would get exactly d points. And also that, so if I pick a point on P1, which is a rational point, then it means that I can pull that point back here, right? And that point will be defined over some degree d number field. And since here on P1 I have infinitely many points, then they will all give me infinitely many points of degree d, not necessarily over Q, but over some degree d number field. So the infinitely many points here, they will pull back to infinitely many degree d points. So then, and this smallest degree d, such that I can have a map to P1, is called the gonality of this curve. And so that's important to understand when we can have infinitely many points on a curve. All right, so I said that already, that if we have gonality d, then we will have infinitely many degree d points. So that's one way to understand. But is the converse true? Not exactly, but we can say the following. So Viray showed that if a curve C has infinitely many degree d points, then d doesn't have to be necessarily greater than or equal to the gonality of the curve, but we have the following bound, that the gonality has to be less than 2d. So then, if I give you an example, then it will say that if I look at the modular curve x1 of 32, this has gonality 8. Hence, if I have a point of order 3, which I don't know if there is or not, on this curve, then it would be sporadic, because there cannot be any infinitely many points of that degree by Viray's result. So that would be such an example, but we don't know if there is or not. All right, now we can talk about the sporadic points. All right, so this is the first example of a sporadic point that Neumann classified the torsion subgroups of elliptic curves over cubic fields, where he starts with an elliptic curve defined over rational numbers. And he found this example that this elliptic curve is actually represented by a point on x0 of 21. So this actually has a rational subgroup of order 21, and it's cyclic. And so he showed that this subgroup is actually just defined over a degree 3 field, which is given here. And we know that there are only finitely many such points. We don't know how many, and it's assumed to be just one, but it's not proven yet. So that's an example of a sporadic point on x121, and it has degree 3. And the gonality of this curve is 4. And that's known to be the smallest integer where we can have infinitely many points. Another example is that there are known sporadic points on x128 of degree 5 and x130 of degree 6. And so what I'm going to say next is that degree of a point is very related to the field of definition of a point, and which relates you to the Galois group. And so we know that the Galois group acts on the points of order n on an elliptic curve. So that takes us to Galois representations. So the connection is that if you're looking at a sporadic point, that just means that on x1 of n, you get a really low degree, unusual low degree point. And that just gives you unusually small Galois representation. So one way to understand that is then looking at the Galois representations of elliptic curves. And that's what we're going to do now. All right, so then if I look at the kernel of multiplication by n map on E, so this is basically the set of points with order dividing n, not necessarily n. E of n, and we know that it's two-dimensional space. It's isomorphic to z over nz plus z over nz. And if I look at the action of the Galois group on this space, that gives me a representation given by from the Galois group to automorphisms of this space, which is isomorphic to the invertible 2 by 2 matrices with z mod n coefficients. And so we can do this for any number n, but we can also do it if you fix a prime L, then you can do this representation for every power of this L, and you can put them together and you get an elliptic representation of this elliptic curve. And so that's given by from Galois group to GL to ZL. All right, so this is called the elliptic representation, and the first one is mod n representation. All right, so Sarah proved that if you fix an elliptic curve E, then there exists a constant C depending on this elliptic curve, such that if you look at this elliptic representation, it is going to be surjective for every L greater than this C. So now the question is that here, well, Sarah asked this question, if we could take this constant not depending on E. So if we could find a constant C that just works for every elliptic curve, so that we will get a surjective representation. So in other words here, if you get a surjective representation, that just means it's big. And remember that I'm looking at a small representation. So those are not the primes that I'm interested in. So then Sarah says that, well, can we find a bound C that doesn't depend on E? And if you take this number field as Q, then the guess is C equals 37. And it's there is lots of evidence in this case that actually 37 works. All right, so then we can formulate this as a conjecture. This is called a Serre's uniformity conjecture, that if you fix a number field K, then there exists a constant only depending on this number field, so that for every non-CM elliptic curve, the mod L representation will be surjective after this bound C. And you can also formulate a stronger version of this, that this constant only depends on the degree of the number field, not the number field itself. All right, so. All right, so then this is just a definition. If I take a point on x1 of n that represents an elliptic curve attached a point, right? So then I can talk about j-invariant of this point as j-invariant of the corresponding elliptic curve. So then if this point is already sporadic, then we say its j-invariant is sporadic. And so this is what we prove. Prove that if you assume the uniformity conjecture, then we show that if you just look at the set of k-rational sporadic j-invariants, that's going to be finite. So one would like to say that just the set of sporadic points itself is finite, but it's not possible for now. But what we can say is that if you just look at the j-invariants of this set, that's going to be finite. And so what we don't know here is that about one j-invariant, you may have infinitely many points. And in fact, that they may be true for CM elliptic curves. But in this work, mostly we focus on non-CM. Maybe one thing to say now. So the CM elliptic curves are more likely to give a sporadic point because they have smaller Galois representations. And so we exclude those and we look at the non-CM curves. All right, so before, I'll just say a couple words about the proof. And so before that, I'll look to say what a level of a Galois representation is. So here in this picture, we're looking at the Galois action on the elliptic Tate module. The first one is going from the Galois group to GL to ZL. So that's the elliptic representation. And so we can also look at mod L representation, but in the middle, we can also have mod L to the n representation. And so what this says here is that if I look at the image of the Galois group here, say I'm looking at modulo L to the n, if I take the inverse image of that, so this is a Serre's theorem, part of Serre's open image theorem, that there exists some n such that pi inverse of image of the Galois group will be the image of the Galois group above one level. So here I'm trying to say, let me, I should have put one more level in there. So I can write. So if you look at the action of the Galois group here, so the Serre's open image theorem tells you that there exists some n such that if I look at the image of this group, which I'll call here as Gn, this is the image of the Galois group under this action. And if I look at this map pi and take the inverse image of this group here, then that gives me the image of the Galois group here. And I'll call that G. So there exists such n so that I know that this happens. So, and that n is called the level of this representation, or the smallest such n. Any questions so far? All right, so then, so what we do here is that, so we basically say that if I have a prime where I have surjective Galois representation, I can get rid of it because it's just big. So what you do is you assume that you have a sporadic point on x1 of n. So then this point, we can assume that it's given by some pair, elliptic curve E, and some point of order n on it. Then if this is sporadic, then you say that, well, it's given by this elliptic curve, so I look at its Galois representation. I know by Serre's theorem that it will be surjective for infinitely many primes. So I take those finitely many primes that it's not surjective. So this says that if I have here some L, that this elliptic curve has surjective representation at this prime, then I can actually just avoid it and say that it induces another sporadic point here on x1 of n. So here, this is still sporadic. And what I know is that the j-invariant of this point and its image are the same. So then if this is a sporadic j-invariant, this is still a sporadic j-invariant, and it's the same. So then this means that I don't have to actually just, if I'm looking at the sporadic j-invariants, then I don't have to look at this big number, but I can get rid of all the surjective primes and get a small number here that I can focus. And so this is one way to make the values smaller. So look at all the surjective representations. And what else we can do? We can also look at the level of this representation. So if I have, let's say that I'm focusing on one prime L, and if I know the level of this representation of this elliptic curve at this prime is n, and if I have a sporadic point on x1 of L to the some power greater than n, then I can lower myself to n, to the level of this representation. I don't have to go that high. I can just deal with this smaller number. So here, everything is just about a fixed elliptic curve. So far, I'm not using anything about the uniformity conjecture. But what we need to do is that, so we have this level. This is for every fixed elliptic curve. But to uniformize this, we need the uniformity conjecture. To find a level that works for every elliptic curve, that we need the uniformity conjecture. And that's what we do. All right. So then, one more thing that we can say is that if I focus on just the rational j-invariants, so we can have a sporadic point of any degree, but I only assume that the elliptic curve given by this point will have rational j-invariant. So if I focus on those, I can say a little more because we know more about the Galois representations of elliptic curves over Q. So then one thing that we can say is, this is another magical number here, that for L equals 37, x1 of L has a sporadic point, and that's actually the only prime that we can get a sporadic point. So in this case, this point is given by, again, an elliptic curve defined over Q, which has a rational subgroup of order 37. And that's all. And in general, for composite numbers, we can say that, so this is not quite right, it is conjectural, but we can say that we can only focus on the primes where we have 2, 3, and some extra prime, which is less than 37. And because I'm assuming here that the Galois representation will be surjective for every prime greater than 37. So then I can just focus on these primes, and we can actually just find a bound for power of each primes. And so we can say that if you're looking for a sporadic point, this is where you should look at. And that's all I'm going to say. Thank you.
Any questions for Özlem?
So there was this bound you showed us 2D for gonality number. Do you know, or possibly does your method tell you anything about, like if I look from 1 to 2D, which number can appear as a degree, or which one not? I'm asking for something either average or statistical thing. Especially I'm asking because they're very related to this Galois representation, and we know quite a lot about them.
Sorry, so which
example,
page is it? Which bound are we talking about?
You had a bound, and it was not your result, someone else's result.
Merrill's result
Yeah,
on the torsion subgroups?
Yeah. So you have a bound that is 2D. Let me just say that, okay, if number 5 is less than 2D, does that ever appear for any elliptic curve as a gonality degree or not? Can this kind of thing be answered through especially understanding of Galois representation?
So in general, I guess I can say that the gonality of a curve is, so for x1 of n, if you fix that curve, then the gonality is not known for every n, or even for the small values. I believe that it's known for 1 up to 40, that we know what the gonality is. And above 40, up to some certain number, maybe 120, that we only know an upper bound, I believe, or a lower bound. Can't remember. But it's not really a great bound. So we don't actually know what the gonality is. So it's a bit hard to decide when you have a point that's going to be a sporadic point or not. Yeah, but this one only sort of tells you that if it is really small enough, then you know. Yeah, but there isn't so much known. So there isn't really so much work done about sporadic points either. So there are different definitions of sporadic made by a couple different people, but this might be like actually the first work sort of focused on that.
Mr. Like this Viray, the case d equals 1 of Viray is essentially Falting's theorem, right? I mean,
Yeah, so this is actually sort of like a corollary of Falting's theorem.
okay.
Yeah, I should have said that.
Okay.
Yeah.
So the gonality, if there's infinitely many degree d points, then the gonality is at least d, right? So between d
It has,
and d,
if it has infinitely many degree d points,
yeah, is the gonality at least d?
no, I think. Well, it can be, So I guess that you can have something like, you can have maybe a morphism from your curve to an elliptic curve which has infinitely many points, and this degree could be less than the gonality. So for gonality, you're restricting yourself to morphisms to P1, but maybe you could have an elliptic curve here with less degree where you can still pull up your infinitely many points. Yeah.
And on your final slide, so you said there is such a point. Is there just a single such one in the L equals 2?
And in the final slide?
Yes. So there is one, and is the curve particularly interesting, and then the other way?
Oh, the 37 one?
Yeah, yes.
Yeah, so this is sort of interesting because it's just there's only one prime that gives you this. And so in this case, we actually know the elliptic curve, we know the j-invariant, and other than that, we don't get any sporadic points. Yeah, so we know what that is. Yeah.
And you had this, the j-invariant being the same, but you were wondering if there could be infinitely many.
Yeah, so
Do
it's,
they all be twists of each other then, or whoever?
yeah, they will be twists of each other. So I guess, so it just means that you could have something like x1 of, for example, for 37, we do have a sporadic point. So we don't know, maybe we have some sporadic point here, and then this will map down to x1 of 37 squared, and then it will map down to x1 of 37. So this kind of picture can happen. So then you would get, so all these points that are mapping here will be the same j-invariant, but then at each level here, you will get an infinite a sporadic point. So you may actually get like a tower of sporadic points with the same j-invariant, and so that will give you infinitely many of them, but we don't know if that actually happens or not, but it could. Yeah, that's why we can just say that at least the j-invariants, if you just look at that set, is finite, but we don't know if we can say necessarily that set of sporadic points is finite. Should we go to lunch?
Any more questions? All right, let's thank Özlem again.